So you have polygons with land cover data, and then you have a bunch of points, and you want to find out the land cover data associated with each point. We're doing a little bit of a funny way because we don't actually have vector data that we're interested in. So I'll try to explain. But here I'm reading data. I'm calling it LULC, land cover, land use land cover. I'm reading the data here. And then I want to know what class is this, or what's the data type, which tells me how I can interact with it in R. And we see this is a spatial polygons data frame from the SP package, or it's a SP object type. SP preceded SF as the primary data structure used for spatial data. So a lot of the times, since you have packages that still use SP and other packages that have moved on and use SF now, you have to go back and forth between them a lot. So what we want to do next is we want to sample those polygons, and I'll display them so that it's clear what's going on. But the first sample, we're doing a regular sample, and so you'll see when you see it that it's not totally random. It's systematic sampling. The second sample is going to be actually random, and you can see that with the parameter type equals random. And then the last one is stratified. And so this function, the SP sample, is taking that polygon data, LULC, and just generating 300 points for us. And then this is adding the land cover class to each point, like a spatial intersection. So if you're in GIS software and you have polygons, you have points inside, you get the class from the polygon associated with each point. So we can run that. And you can see after I ran that, they popped up in my environment here. So I can always see. This actually gives me a lot of useful information. It's a little difficult to see here because, well, we only have spatial data now. So right now it's only telling us I have spatial points here, I have a data frame there, but you'll see later it'll tell us other useful information. So I want to plot what we just did. And this time I did not split the screen, I just plotted each one individually so that's nice and large. And so I can toggle between them like this. If I turn this into an HTML file, they would be listed one after the other. So that can be a pro or a con. This is, but you can see here we have the polygons outlined in red. So here's a pretty big one there. They're pretty small and they're kind of all over the place. And then next we have our regular sample. So they're not random. They're obviously in a pattern here. So that's our rate. They're kind of covering each other up. And then we have stratified, and that looks different still. So depending on what you're trying to do, you're going to use a different sampling technique. And then last, we want to extract the reflectance data from the pre-prepared Landsat data associated with each point. So we just run the extract function. We pass in our Landsat data. We pass in our points. These are the regularly sampled points. These are going to be the reflectance values associated with the first sampled point. These are the reflectance values associated with the second sampled point, and so on. Compute the mean reflectance values for each class and each band. So you can see the last parameter here is function mean, and we do that for each class. And then the aggregate function automatically takes the columns. The first thing we did is we just set the row names to the land cover type. And so now we can see that for the built land cover type, the mean reflectance value was this. For band 1. For band 2, it was this number, and so on. So if we were going to plot that, which is going to be the more meaningful way of seeing the data, then we get the mean, so the mean reflectance values for each band, and then each line corresponds to a different cover type. So you can see that, you know, cropland has a peak here at, for band 5, the reflectance values are much higher than anything else, and you can, probably the most difference between the bands are between 4 and 6. Just doing basic like NDVI. So this is a function to compute NDVI. It's really simple. The point is just that you can do raster algebra in R. So we can run that. And we get a lovely NDVI. It's just a nice little histogram of NDVI values. You can reclassify rasters, and so if we want to specify all of the vegetation, for example, if we have an NDVI value less than 0.4, then we know it's not vegetation, so, or probably not. So we're going to just set that as NA and then only plot vegetation, what we think is vegetation. And then this is still the NDVI values, it's just only plotting them for anything greater than 0.4. We can classify based off of different NDVI values, I think is what is going on here. And so this is saying anything between, you know, negative infinity to 0.25, we're going to set as NA. That's not anything that we're interested in. Between 0.25 and 0.3, we're going to set to 1. And so that's this yellowish color here. And then anything between 0.3 and infinity is NA again. So we're only coloring this, the yellowish thing is the NDVI values between 0.25 and 0.3. So if we go back to the original NDVI map, here it is. That's going to be this light green color here and up here. So the idea is, you know, what is this? What should we classify it as? And we can plot that over our original data. And so here I have the red, green, blue plot for Landsat data with just true color composite, and then we plot that reclassified data, this over top, and I added a transparency of 0.5. So that yellowish speckle here, and in the top here, that's that stuff. And so the theory is that's bare land, or maybe urban area or something. So that's nice. You can overlay images. Yay. We want to do some PCA. So in order, because the raster files have so much data in them, we're not going to use every single point. We're going to randomly sample 10,000 points. So we got a good chunk. And we want to display a near infrared red plot. So we're just using bands 4 and 5. So we're calling our sample SR. So we want to do a scatter plot of the points that correspond to the near infrared and the red images. But because we have 10,000 points total, it would be really dense. And so I did the smooth scatter instead of just the regular plot. And we get this nice, you get to see the density. So the darker parts are the more dense areas and the lighter parts are going to be less dense. So you get a nice plot there. And then we can do principal components. We're just using the PRComp, principal component function. We have to scale the data. That is always done with principal components. And we just run that and we get our eigenvectors. We can do a summary and see the proportion of variance explained here in the table. And we can do our plot, our favorite plot, and see that it drops off and evens out at 3 or 4. Principal components, as we would expect. We want to create a principal components raster. So we're going to use the predict function. And if I didn't know what to put into the predict function, I can just, so we run the predict. And this is important. So when we did that in the help window, we see that there are multiple functions called predict. And so one, it comes automatically in the stats package, and one comes in the raster package. And we want the one in the raster package because we want to apply it to raster data. So it's always good to know which one you're using. We can get the parameters for this. If we want to prevent the software from being confused, we can always specify the library we're taking of by saying the library name, : and then the function name. So in the predict function, then we have our raster, our original raster data, the PCA model, because, and we know we put the model in because that's specified here, and it automatically extracts the, what do you call it? Equation, I guess. Equation to apply. And then the index, what is the index specifying? So this is basically what I do all day. The index, it's an integer. It selects the columns to use if the predict model returns a matrix with multiple columns. Depending on what this returns, we might be interested in one or more things. And in this case, we're interested in the first 2 columns. So we say 1, 2, and then we want to plot the first principal component. And it's taking a minute because it's applying that function to all of the different rasters. This does not look super, super informative. I haven't applied any stretching on this, so that's probably not helping. But you can see that the river is pretty clearly delineated. The elevation in the lower left-hand corner is pretty well delineated. So there's some big, like the first principal component is probably just saying, here are the biggest differences between things. Water is really different than everything else. And then the second principal component is a little bit more difficult to say, like, oh, this is definitely just delineating the difference between the river and everything else. And so something that we can do is we can reclassify it. So here we have our false color composite on the left, and then we have our false color composite on the right with the second PCA on top, but reclassified so that between -infinity and 0 is classified as 1 and everything else is NA. So all the dark green areas, the super dark green areas, are going to be NA, and everything else is going to be 1. Basically to summarize what PCA2 is telling us, and then we can overlay that on top of our false color and hopefully get a better sense of what it's representing. So it looks like it corresponds to the river here, and it also is picking up some of that urban area. You can do principal components in R on rasters. That's the point. This is using RS Toolbox, which is built on top of the raster package. So it uses a lot of the same data structures, which is great. But it has more tools specifically for spatial data, for remote sensing data. This is taking some Landsat data that is included in our RS Toolbox specifically for demonstration purposes. So here the nice thing is it uses the metadata file in order to load everything. So instead of needing to have like 10 file names or 11 file names for each band of Landsat, I can just give it the metadata file. This is older. So it's using the mtl.text. In order to use RS Toolbox, you need that. You need that mtl.text. You read the metadata file, and then you're able to it just reads the metadata file, and it gives you your Landsat data. So here we can see LSAT is a raster stack. We can inspect the data. It's a raster stack. So here we just have 7 bands. The important thing here is doing atmospheric correction. So, so what do we have for atmospheric correction? Limited options. We can scroll down to details. Oh, I see. Okay, 4 atmospheric correction options, or you can just convert to radians. So those are, that's what you have. These are pretty much the options I've seen in other packages as well. If you wanted to do something different, you'd have to either find a package that does it or implement it yourself. When we first printed out the raster information, you see our min and max values, our integer numbers. Once we convert them, now we have decimal or float numbers. You can print the metadata if you're interested in it. This information, the offset and gain, is used, I guess, in the atmospheric corrections, and so that's very important. So some of the packages will have you actually input that into the function yourself. So you have to know where to find it in the metadata. We can do a cloud mask. So this is this guy's method. He says this is a pretty rough method of doing a cloud mask, but it works if you don't need something more sophisticated. What they're doing is this is just doing using the blue and another band to figure out where there's likely clouds, and we think there's clouds where these black spots are, and so we choose the threshold value appropriately, and we can create a little cloud mask, which you can see in yellow here. So our original data had white spots. Now we have a mask of covering it up. We can do basically the same thing to do a cloud shadow. You can specify where the cloud shadow is using like actual values. But I thought it was easier to do this interactively. You display it, you just use your cursor to click the cloud, click the shadow, click the cloud, click the shadow. And then it's good. You combine your cloud mask and your cloud shadow mask, and now we have a cloud shadow mask. The last thing I wanted to do was just taking the tools we've already seen and then do it with data from Lake Erie. So here I'm loading the RS Toolbox, Raster Viz, and the SF package. I downloaded this from I think it's Earth Explorer, Landsat data. So I'm just gonna read that in. Well, digital numbers here, we can see, all of the regular information that we normally have. We have 11 bands. I did just dark object subtraction, atmospheric correction here. There weren't a lot of clouds or anything, so it should be pretty good. Now we have atmospherically corrected data. So I just ran this to plot. It's a pretty big file initially. I do crop it later, so that's why it's taking a minute to plot. So we can see, the Western Basin is what I was focusing on because that's where we have the EPA data. Here we've got the histogram stretch. We see a little bit more difference, I think, in the watercolor here, which is kind of nice. And our land doesn't look blue. We can do false color. This was my favorite because you can clearly see the difference between the vegetation and the water now. Here I'm doing the pairs plot. So this is nice pretty much what we would expect. Bands that are close together are more similar than bands that are not close together. So here what I'm doing is I'm using a package called readXL to read Excel files. So then we can display just the first 6 lines, and we see we have dates, the EPA stations, all of the data is here. We can use this arrow. We have a lot of variables. And what we want to do is we want to take the Landsat data. Well, we want to get reflectances from the Landsat data for the date that we have, the comparable date that we have EPA data for. The closest date we have is July 15th. So I think the Landsat data was from the 16th. So just one day off. Here, what I'm doing is I'm just getting just the data for 7/15. So once I do that, then we can see that the only date in the EPA data is the July 15th. We can see the only date we have here is the 15th in that date column. I took the station data, we had longitude and latitude for each station, and I turned it into a shapefile. So we can just read that in. So this is an SF format. We have the station name, the geometry column is what really matters. And so each of these is specifying one point that represents the station. Here I'm just transforming the coordinate reference system of the station data into the coordinate reference system for the Landsat data. Here I'm just turning our SF data, which we saw here, simple feature, into a SP object. So we can print that. And now it's a spatial points data frame. So that means that now we can use it with RS Toolbox. I'm gonna plot our Landsat data and then with the stations on top. So we can see where the stations are. So I'm just gonna take my plotting function, like I did before, in the console. I'm gonna print it out so it shows up on the right-hand side. And then I wanna do E is draw extent. And we just wanna get this area where the stations are. That should be good. So now I have my extent that I want, and I'm gonna crop it. Okay, so now we get the EPA points on our cropped image. But we don't just need to see them, we need the reflectance data from each point. So we're gonna use the extract function like we did before. So extract from our Landsat data at the station locations. And then I'm just setting the row names to the output to the station name so that it's easy to read. We have reflectance data for each station. What we want to do now is we want to take this data and we want to put it into our EPA data frame. And then I'm just going to merge them. Take all the EPA data, take all the data, DF data, the reflectance data, and then just combine them when the stations match up. And then we're just gonna check, make sure that nothing funny happened. So here I have WE2, here's the data for WE2, and then I can just check at the end of this data frame. Band 1, 0.12, 83735, great. Band 2, and we're just gonna look at the surface data. But what we really want to know is the satellite data correlated with CHLA and which ones? And actually it's kind of surprising. We got these thermal bands here that were pretty strongly correlated compared to everything else. And so, but a lot of correlation between bands, but not a lot between the CHLA and PC and the bands.